Chapter 9, Section 7, Practical Applications of Inner Product and Vector Space. In this section, we talk about how inner product and vector norm are used in real-world data science project. Let's begin with a basic idea. A vector space is a mathematical structure where we can add vectors. We can scale vectors. The result still stays within a space. This may sound abstract, but you are already using it every day in data science. Let's consider an example of a customer's movie preference. Suppose we track users based on how many action, comedy, and drama movies they like. If you add them together, A plus B is still a vector in the same space. It represents a new combined user. If we scale user A by 2, it is still in the same space. This means these vectors form a vector space. The concept of vector space is useful in data science because any machine learning algorithm that works with numerical data relies on this structure. Let's see this using an example of linear regression. Let's say we are trying to predict someone's monthly rent based on the size of their apartment and the number of rooms. Here is how the data might look. Now we can represent each apartment as a vector of features. Each of these is a point in two-dimensional space where the horizontal axis is size. The vertical axis is rooms. So our input data, called predictors or features, live in a vector space, a space where we can add vectors. That is, we can combine effects from multiple apartments. And scale vectors. That is, we can apply weights to features. This is exactly what linear regression does. When we do linear regression, we assume that the output variable y is a linear combination of the input features. In vector form, we can express it in this way. Here, w is the weight vector, and x is the feature vector. All possible predictions our model can make are combinations like this expression. So, our regression model is trying to find the best linear combination of these feature vectors to match the actual y values. This entire process is happening in a vector space because we are adding vectors. We are scaling vectors, and the results still live in the same space as your target values. Let's say we are trying to find the best combination of size and rooms to predict rent. We need a space where adding size and rooms vectors makes sense. Scaling size by a weight still gives a valid vector, and the model can search freely over combinations of features. This is only possible in a vector space because vector spaces are closed under addition and scalar multiplication. If our data do not live in a vector space, linear regression will not work. The model will not be able to form linear combination of features, which is its core operation. So, in the context of vector space, our input data are vectors. Linear regression is to find the best line or plane in that space. The set of all possible lines or planes is a vector space. Without a vector space, regression cannot even form a model. So, what does a linear regression try to do? Imagine you have feature vectors and target outputs. we want to find a function like this one. Here, W is a vector of weights. The goal is to make the predicted length y hat I as close as possible to the real length yi. To measure closeness, you use the difference. We can square these differences and sum them over all the data points. Thus, the loss function can be defined in this way. This is called the mean squared error. Now, where does the inner product come in? Look closely at the formula. This is an inner product between the weight vector W and the feature vector xi. Formally, it can be written in this way. So, every time we calculate the predicted value, we are taking an inner product between the model's weight vector and the input vector. The inner product measures how much the two vectors are aligned. If W and xi point in the same direction, inner product is large and positive. If they point in opposite directions, inner product is large and negative. If they are perpendicular, inner product is zero, meaning that the input and output have no relationship. Thus, in linear regression, the model aligns itself to the features xi, so that the inner products match the output yi as closely as possible. There is a plane formed by the feature vectors x1 and x2. Let's simplify this to a two-dimensional plane. In reality, this is a plane made up of high-dimensional vectors containing many observations, but for simplicity, we will represent it as a two-dimensional plane. The observed value y is floating somewhere above that plane in the space. We drop a shadow, y hat, onto the plane. The error vector y minus y hat extends vertically from the plane. So the distance between y and y hat is minimized. That is why the prediction is optimal. Mathematically, the best prediction y hat is the orthogonal projection of y onto the space spanned by the feature vectors. Orthogonality here means that the error vector is perpendicular to all feature vectors. The error vector represents the difference between y and y hat. Perpendicularity is defined by inner products being zero. Thus, linear regression finds y hat that satisfied this condition. Let's summarize the roles of each concept in linear regression. Vector space holds all the possible combinations of features and predictions. Inner product measures alignment between weights and features to predict the target. Projection finds the best approximation of the target in the feature space. Orthogonality guarantees that leftover error is unrelated to any feature. Linear regression lives in a vector space. Inner product is used to predict and to measure how good the prediction is. The best prediction is found by projecting onto the feature space using the inner product. Without inner products, we would not have a way to define closeness, projection, or error in linear regression. Thank you for watching. Please thumbs up and subscribe to my channel.